We present Neural Gaits, learning bipedal locomotion via control variable functions and zero dynamics policies. We develop a method of generating dynamic walking behavior for a planar biped by incorporating three major components. First, we frame walking as a set invariance problem enforceable via control variable functions. Next, we encode walking through a policy defined on the underactuated component of the robot, the zero dynamics. We then test the policy on the physical robot and use the hardware data to learn a residual term for the zero dynamics. This process of training a policy and learning a residual term is repeated episodically.
We begin by discussing the necessary details to frame walking as a set invariance problem. As walking robots experience intermittent phases of continuous and discrete dynamics, they are naturally modeled as hybrid systems. As such, various continuous time and discrete time conditions need to be satisfied in order to generate successful locomotion. Two continuous time conditions were created: maintain the angle of the torso in a range and keep the swing foot of the robot in a tube. The two discrete time conditions were that the joint angles must be symmetric before and after the impact event, and the leg must be in front of the robot at impact. In order to understand how these conditions are enforced, we must understand the notion of control barrier functions. Let H be a continuously differentiable function, and C denote the zero superlevel set of the function. The set C is forward invariant if the following algebraic condition is met. The time derivative of H must be greater than or equal to some class K function of H itself. For discrete time dynamical systems, a slight modification is needed to the barrier condition, where the time derivative is replaced by the discrete update map. Therefore, to encode the continuous and discrete time set invariance conditions, we enforce them as barrier functions over the phase space. These are written down as candidate barrier functions, as a random controller will not satisfy the dynamic equation. Our goal is to find a policy which steers the system to satisfying the constraints. Next, we must understand the zero dynamics of the system and how our policy is trained. We begin by writing down our desired outputs that we would like to converge to zero. In our case, this corresponds to the joint angles of the robot. Then we can select additional coordinates corresponding to the underactuated states of the system, denoted as the zero dynamics coordinates. Specifically, the linearized position of the hip and the horizontal angular momentum were chosen. Given these coordinates, we can construct a differentiable function phi from our state space to our output and zero dynamics space. In doing so, we can define the zero dynamics manifold, the surface on which the control input does not appear. Associated with this manifold is the projection of the dynamics through phi, known as the zero dynamics. As phi is bijective, its inverse is well defined, giving us a mapping from the zero dynamics manifold to some submanifold of the original state space. This is key. If we can ensure that the system behaves well on the zero dynamics manifold, specifically if we can ensure that the zero dynamics satisfy our previously defined barrier functions, then we can make guarantees that the full order system will similarly satisfy our set invariance conditions. As such, we can refine our definition of the policy to only be defined over the zero dynamics surface.
An iteration of the learning process is as follows. First, fix a policy YD mapping from the zero dynamics space to the desired output space. In this work, this was taken to be a neural network with associated weights theta. For the first iteration, the weights were randomly sampled. Next, given the output, we can write down our zero dynamics z dot, which importantly are a function of the chosen weights. Let V denote the magnitude of the violation of the barrier inequality condition at a point z. We define the barrier loss as the spatial integral of the barrier condition violation over a zero dynamic space. In practice, a Monte Carlo sampling approach is used to approximate this integral, which defines a loss function we can backpropagate through to update the weights. Note, importantly, that no temporal integration is needed in the training of this policy. Only sampling over the lower dimensional zero dynamic space is required. Here, we see a closed-loop simulation of a random policy on the robot. These are the iterations of the learning process in action. In the upper left, we have the barrier violation over the zero dynamic space, only evaluated over regions of positive orbital energy. In the lower left is the evaluated loss. In other words, the approximated spatial integral of the barrier violation over iterations. On the upper right are the barrier violations as a function of time for each iteration, and on the lower right are the joint angles as a function of time. As the iterations progress, the robot is able to slowly learn to walk via minimizing the barrier violations. Again, this temporal integration is not needed in the training process, but is simply visualized as a tool to qualitatively evaluate the fitness of a policy. Here is the final trained policy that is able to walk stably in simulation. When the policy is run on hardware, we note that the robot falls forward and is leaning on its supports. This is due to the error between the model used to compute the zero dynamics and the true dynamics of the hardware system. To combat model mismatch, we learn a residual error on the dynamic strain from rollouts of the physical system using the agile method. The update to the training process is simple. We refine our previous policy by training on the zero dynamics augmented with the learned residual. After one iteration of learning with the hardware data, the following policy is realized. Notice the stable walking, but oscillatory output tracking on the legs. This process is repeated once more, and aggressive, stable walking is generated. We would like to thank the sponsors that make this work possible.